Ready to go here. So, like I said, first things first, any questions from things that were assigned yesterday? What you want to go? Any of those probability problems or anything you want to work through? As review, we talked about basic probability. You had to apply some of those concepts to different types of questions. Some of them were pretty basic, others were maybe a little more challenging. Any of those you want to go over? All right. So once again, students will be able to identify sample space, calculate probabilities, conditional probabilities we're going to talk about today, as well as binomial probabilities. Okay. Now, this is a conditional probability formula that you were exposed to last year, right? Because I know we just covered it in Algebra 2. We might have saw it in a little. We might have seen it in a little bit different form. But it says if the event B depends on the event A. We talked a little bit about dependent probability yesterday. All right. This is a formula that we can use to compute conditional probabilities. All right. Now, the way you maybe saw this written in a different form last year. If we did a little algebra here, this is another way we could write this. Right? Because I think this is this form, maybe we saw it last year. Now, just to kind of explain some of this notation here. Sometimes this is what causes a little trouble there. Okay. What does that really mean? What does that probability of B and then that dash A mean? Does anybody know what that means? Okay. Well, that's the probability of B. I'm going to put of B given that A occurred. All right. Probability of B given that A has occurred already. Okay. So we have basically two different conditional probability formulas. All right. Two different conditional probability formulas. All right. So you can use either one. They really mean the same thing. I think in the book, in this specific lesson, I think this is the one they're going to want us to use. But they're the same thing. Hopefully you can see that algebraically. They mean the same thing. All right. So that conditional probability, that's the probability of B given that A has occurred. All right. So we'll be familiar with that. Now, when we're working with problems like conditional probability, sometimes we can take multiple approaches, kind of like we talked about yesterday with respect to that chocolate problem, or that problem with the candy. All right. So, all right. Let's look at an example of where we could use this conditional probability formula, maybe a couple different ways. Maybe we'll look at more than one here. All right. So I'm going to have your books open to page 667. All right. We're going to look at one or maybe two problems, maybe a couple different ways. All right. And I picked one picked a couple from the text because just that way we can, otherwise I have to write all these things out and I don't really want to do that. Okay. Now let's look at number 29 here. And like I said, sometimes there's more than one way we can approach some of these questions. So maybe we'll look at one using that formula, then we'll look at another option. All right, so it says for 29, it's titled piano lessons. It says if it rains tomorrow, the probability is 0.8 that John will practice his piano lesson. If it does not rain tomorrow, then there's only a 0.4% chance that John will practice. All right, suppose that the chance of rain tomorrow is 60%. What is the probability that John will practice his piano lesson? Okay, now maybe this isn't as much, this is kind of conditional probability because we're looking at, what happens depending on if it rains or not. Okay, so this is a kind of a dependent or conditional situation. All right. Now, sometimes when we're looking at these types of probability questions, one option to use to solve this would be a tree diagram. Okay, so sometimes you could use a tree diagram. You don't have to use a tree diagram. It just might be the way to go in some cases. Might be easier to understand. So for our tree diagram, I'm going to set up our first two branches, and it's going to be whether it rains or no rain. Okay, so what's the probability that it's going to rain tomorrow? They gave that to us in the problem. What was it? So I'm going to put 0.6, which means probability it doesn't rain is 40%. Agreed? That kind of comes from the other one. Now, if it rains tomorrow, the probability is 0.8 that John will practice his piano. So he's either going to practice or no practice. So if it rains, obviously he's going to be stuck inside. There's an 80% chance that he's going to practice his piano, which means that there's a 20% chance that he will not. Okay. Now, if it does not rain, what's the probability that he practices piano? If it's not raining, he's probably going to go outside. He'd be more apt to go outside. What was the probability that if it, let's see here, what are we looking at here? If it does not rain tomorrow, there is a 40% chance that John will practice, which means there's a 60% chance that he will not. Okay, so this is what this tree diagram might look like. And I tried to do it in different colors. Not that that's important, but that might help there. Okay. Now, what are we concerned about in this problem? The probability that John will practice his piano lessons. Well, here's one path where he would practice, right? And here's another path where he would practice, right? So realistically, all of the branches at the bottom there would form a probability distribution, all right? And if I multiply the paths, kind of like we talked about yesterday, this would be 0.48. This would be 0.12. This would be 0.16. And this would be 0.24. Realistically, we've come up with a probability distribution where all of those probabilities on the bottom line there, they should add up to 1, and they do. Right? That adds up to 1. Now, we're concerned about the two paths that would be John practicing his piano. Well, I'm going to say that there's a 64% chance that he'll practice his piano. How did I get that? Yeah, I basically just added these two, paths where he would practice.
What did you multiply again to get the numbers in black?
Yes, 0.6 times 0.8 gives us 0.48.
Okay.
So I multiplied down each of the 4 paths.
Okay.
Yes. Okay. So basically there's a 64% chance that he is going to practice his piano. And I think a tree diagram is a good way to do that. All right. So sometimes that would be a good option to approach a conditional probability, because we're still dealing with what's the probability practice, either whether it rains or whether it doesn't rain. Okay, so a tree diagram can work in some cases. Any questions on that? Now let's look at another one where maybe we could work through the problem, this a different way. Maybe we'll use that formula. All right. Now I chose number 31, I believe. Okay, and we could look at others, and we'll probably have questions to look at tomorrow. Here we're going to use that formula. Okay, and this might take a little more time to go through this one, not because it's more difficult, just because I'm going to try to write things out using that formula. All right, so it says conditional probability. 2 pre-calculus sections at West High School. Mr. Abel's class has 12 girls and 8 boys, while Mrs. Bonitz's class has 10 girls and 15 boys. If a West High pre-calculus student chosen at random happens to be a girl, what is the probability that she is from Mr. Abel's class? All right. What is the probability that she is from Mr. Abel's class? That's the conditional probability statement there. Okay. So if we kind of put that in the context of, this was the formula we were given. I think that's the kind of the form we're given, right? We basically, I'm going to write this out in words because I'd like to do this. Probability, they are from, I'm going to say Abel's class, given that they're a girl. I can't spell girl, I guess. Would be the probability that they are a girl and in Abel's class, divided by the probability that they are a girl. So I like to write it out in words. Okay, I like to write that out in words, right? This is really what the question is asking us to find right here. All right, I'll read that again. If a West High pre-calculus student is chosen at random, happens to be a girl, so we know it's a girl, it's given that it's a girl, what's the probability that it came from Abel's class? Okay. So we're gonna have to find these two probabilities, all right, to help us. All right, so let's do one at a time. What's the probability it's a girl, excuse me, and from Abel's class? Well, there's two classes, so there's a 50% chance she's from Abel's class, right? And in Abel's class, 12 of the 20 students are females. Do you agree with that? It's 50-50 chance that she's in Abel's class or Bonitza's class. That's where that 1/2 comes from. And 12 of the 20 students in Abel's class are female. Okay. Questions on that? So that's going to be that right there. That's going to be our numerator there.
For girl, why wouldn't you just add look at the total people as a whole and then
We're going to do that next. Okay. We just did the top. We're going to do the girl part now. Right? That's what you're getting at? Yeah. So we just did the top.
So why did you did the 1/2 because two classes?
There's two classes. Yes. We'll take into account the kind of the weighting of the classes differently because there's not equal boys and girls. That'll be taken care of in the bottom. Okay. Good question though. So now what she was referring to as the probability that it's a girl would be, it could be a girl from Abel's class, right? Or it could have been a girl from Bonitza's class. And how many girls are there in that class? 10 out of the total of 25. That's taking into account it could have been in either class because we could pick a girl that's in the other class. All right, so that's kind of taking that into account. So realistically, the probability we are looking for is that fraction right there, isn't it? The probability she's a girl and from Abel's class divided by the probability that it's a girl. All right. And if we do that correctly, I think, if you evaluate that, I think you get a 60% chance. Right? That's just computing those fractions there and adding things. Okay, that's purely computational. The tough part would be getting that set up. Okay, the tough part would be getting that set up, I believe. Okay. So there we use the formula rather than using a tree diagram. Could we probably use a tree diagram? Yeah, probably could. Right. But I want to make sure I show you different options here because some people like formulas, some people like tree diagrams. Okay. Questions on that? All right, so conditional probability, like I said, when I'm working on those, I honestly try to do what I did here. I wrote down the formula that we're using for conditional, and then I put it in the terms of the problem we were given. Does that make sense? If we just say A and B, we have to remember what A represents and what B represents. I think putting it in the terms or the vocabulary of the problem you're given will make it easier to understand. Right? That's just my opinion. Okay, so writing things out isn't a bad idea in words. Right? It'll never be a bad idea. Right, so questions on that? All right. You want to do that? Yeah, we could have. All right, so here's a tree diagram for that one. Yeah, we could. But we're still gonna, it's maybe not exactly the same as the other tree diagram application. It's not gonna be as simple as just looking at the numbers at the bottom. There might be more to it. Okay, so remember, this is what we're trying to find the probability of from Abel's, given it's a girl. So we're trying to find the probability it's Abel's and a girl. This is Abel's, by the way. Divided by the probability it's a girl. So we could find some of those probabilities using a tree diagram. So here we go. Boy, or Abel's class, Bonitz's class, and Abel's class. That's 50-50, right? We talked about that. Now, if it's from Abel's class, if we go boy and girl, I think there were what? 12 out of the 20 were girls and 8 out of the 20 were boys. And for Bonitz's class, if we keep that consistent, go boy and girl here, 15 out of the 25, is that right? Or no, excuse me, 10 out of the 25 were girls, 15 out of the 25 were boys. So we could use the tree diagram to help us find these two. All right, we could help us to find those two values. The probability you're a girl would be those two paths right there. Oops, that's a boy, by the way. That's doesn't make any sense, does it? Sorry. I shouldn't have circled that path. Okay. Probability it's a girl would be this path or this path, which would be 1/2 times 10 out of 25 plus 1/2 times 12 out of 20. Okay. I'll circle that right there. All right. So that's going to help us find those values. So it's going to be a little bit different application, but we can still use that here. All right. And I could write those numbers down here too. You know, I could find all of these values down here. It would just be multiplying a path, right? Like we did earlier. Now, what's the probability that it's somebody from Abel's class and a girl? Is that this path again? And is that really the same thing we just had? It is, but if the tree diagram makes more sense to you, great, that's fine. All right, so do you see that's a little bit different than using, I mean, you can still use the tree diagram, but you have to use it to find what you need for your formula. It's a little bit more to it. Okay. Okay. So if that helps you find those individual probabilities for the formula, that's not a bad idea. Okay, so do whatever you have to. Tree diagrams aren't a bad idea. The problem with some tree diagrams is they get so big. These ones don't, right? If there's really only a couple things going on, they don't get too big. What if there were 4 pre-calculus tests or classes? Would that get more expansive? Yeah, it probably would. You could still do it, but you'd need more space. Okay. Other questions on that one? Yep.
For tree diagrams, can you have more than just like the original two at the top? Like say it was 4 pre-calc.
You would have to have, yeah, you would have to have
Just
4
have four
branches.
different
You
offsets.
you would have to have 4 branches and the probability would be 1/4 for each of those, right?
Yep.
And then you'd have 2 branches off of each of those 4.
Okay.
So you'd have
If it had
8.
to start with.
Yep.
like that.
No, you don't, you wouldn't have to. Well, there'd still be a peak, but it'd be a peak with 4 of them.
Yeah.
Yeah, if there were 4 classes, you'd have to have 4. If there were 3, you'd have 3 branches coming down. Yep, that's fine. You just adapt it to whatever type of problem you're dealing with. All right. Good questions. So that's that conditional probability formula. Remember, we can look at different forms of that. Now, binomial distribution, we're talking about probability, right? We talked a little bit about binomial expansion or binomial theorem back in section 2. Here, we're going to apply that to a probability situation, okay? Anytime that there's either basically when we're talking about binomial, they talk about success and failure, okay? Success and failure are the 2 things you're going to be dealing with. Yesterday, the example we gave was Peyton shooting free throws. Remember that? Success would be making a free throw, failure would be missing it, right? Whenever there's some type of a problem or some type of an experiment, when there's just 2 things that can happen, binomial means 2, right? You can apply this, okay? Now, just some underlying things we want to make sure we're familiar with. Using this formula down here, and we're going to use it in a few minutes together. Don't worry about that. The probability of a success is P when we're looking at this formula down here. And like I said, we'll use it. The probability of a failure, they're saying, is Q. All right. So this looks, let me get this out of the way. All of this right here, people, that looks a lot like what we did. It's got different variables there. It's got P and Q, but doesn't that look a lot like what we did with binomial expansion? Okay, it does. Okay, it's really the same thing. All right, it's really the same thing. Okay. For example, this is in more general terms. We're gonna apply this in a few minutes here, and I'll use the same notation. It says the terms in the binomial expansion of P plus Q to the n give the respective probabilities for n minus 1, so many successes. Okay, so it's written in general terms. Okay. All right, so how do we use that in a problem here? This is going to be similar to what we saw yesterday, I think, but anytime that there's success or failure, yes or no, okay, we can do that. All right, suppose Tommy makes 92% of his free throws. It's a free throw problem again. We don't have to always use free throw problems, but we're doing this here. All right, if he shoots 15 free throws and if his chance of making each one is independent of the other shots, what is the probability he makes all 15? Well, how could we use this to do that? Well, common sense wise we would say that there's only one way he can make all 15, right? But then the probability he makes an individual free throw is 92% if it's independent of the others. And how many factors of 15? How many factors of this would we have? I just gave it away. 15. All right, so that would basically, this would work out to be 0.92 to the 15th power. Okay. Now, how do we use our little formula for binomial probability here? All right. 15 shots, he's going to make all 15. Probability of a success is 92%. That would be 15. Probability of a failure is 8%, and that's 0. That's going to lead us to the same thing, isn't it? This is really, how many ways could you make all 15? One way, right? It's only one way. You make them all. Right? This is like that P to the, 15th power. This is like the Q to the 0 power. 15 successes, 0 failures. Does that make sense? Questions on that?
Where did the 0.08 come again?
Well, if he's got a 92% chance of making it, he has an 8% chance of missing it. And realistically, in this problem, do we even need this piece? Because it's going to turn itself out into 1, but I put it there just for the sake of, you know, discussion there. All right, 0.08 to the 0 power is going to be 1. We don't really need it, but like I said, I'm putting it there for your benefit. All right. And they wrote it as 0.92 to the 15th power with about a 28.6% chance that he makes all 15. He's a pretty good free throw shooter, so it's fairly likely. All right. Now, it might be more valuable to look at this one. Suppose Tommy makes 92% of his free throws. If he shoots 15 free throws, and if his chance of making each one is independent of the other shots, what is the probability he makes exactly 10? Here, we're going to have a little bit more, you know, we have to use a little bit more of our understanding of the binomial distribution. So he's going to take 15 shots. We're going to figure out the probability of him making 10. So there's basically, that's the combination of 15 shots and selecting 10. Basically, it's slotting those misses in 10 of the 15 slots. Okay, that's how many ways that could happen. Now, that means there would be 10 successes and how many failures? 5, right? It's kind of like with that binomial theorem, our exponents here are going to have to add up to the number of trials, right? The number of trials is 15. So I think this problem's maybe a little more valuable than the last one because we had a mixture of successes and failures. All right? Keep in mind, this is just an alternate notation for what? For this, isn't it? So it's a combination. Remember we talked about that in section 2?
So when you put it in your calculator, you put it in like that?
You probably have to put it in like this. Yeah, but I just want to make sure that you're familiar with that's what it's representing. Okay, and I think we talked about that in section 2. All right, I believe we did. So another way to write it would be like this. And this is maybe the way you're going to have to write it in your calculator. But what does that give us as a probability? What's the probability he makes exactly 10? Can you find that number? Let's see if you can do that. I don't know what it is off the top of my head. What's that number there? Anybody have it? I'm asking you to compute this. Try it. Everybody should try it. Some of us just sit back and make other people do it, and then we don't know how to do it when we have to do it on a quiz. Take the 2 minutes it takes to do this. Okay. Make sure you get the same number. Okay.
0.00427.
0.00427? Yeah. All right, and I can get rid of all that stuff there. But you can say they wrote it out the same way I did. 10 makes, 5 misses. Okay. 10 makes and 5 misses. Okay. Now keep in mind that's a very small probability, but why is that probability small? We just looked at the probability he made all 15 was pretty high, wasn't it? Okay. Since he's a good free throw shooter, he should make more than 10, shouldn't he? That's why. Do you think the probability he only makes 2 is much, much smaller than this? Yeah. Okay, so it's kind of a spectrum. But if we found the probability he makes 0, 1, all the way up to 15, those probabilities together would add up to what? Add up to 1. Okay. So some of these are going to be relatively small. Okay, some of these are going to be relatively small. All right. Let me have you try to find this one. What's the probability he has, let's go 12 successes. Find that for me, please. I think that should be a little bit higher than 10 successes. 12 out of 15 is what? 80%, it's still not gonna be, he should probably still make more than that. And like I said, I don't know what the answer to this one is because I don't have it. Did we have that number?
0.08.
0.08.
Yeah.
Okay, so it's actually more likely because 12 is closer to his, you know, his percentage. 12 out of 15 is 80%. Is that right? Yeah, it is. Okay, so how would we do that? It would look like this: 15, 12, 0.92 to the 12th, 0.08 to the 3rd. That's how we would get that number right there. Questions on that? So these terms that we could come up with using that binomial probability, they really are the same as the terms using the same patterns you come up with when using the binomial theorem. Okay, you're dealing with combinations. You're dealing with the exponents have to all add up to the number of trials, and then you're just dealing success and failure. Right, success and failure. Remember, success plus failure must equal 1. Right, so if you're given success, you can compute failure. All right, I don't think of it that way. Makes and misses is a better way to say it, but they use it in the term success and failure. All right, questions from anyone? All right, so here's some more questions to look at in section 3. Keep in mind, we've got a quiz coming up on Monday. Tomorrow will be kind of a step back to review section 3. And then Friday is pretty much going to be a day to go over that worksheet. And then, you know, if you have any questions over anything that's sections 1, 2, and 3, you could say, hey, let's do this kind of problem or that kind of problem. All right, it's going to be on what you want to go over, not a bunch of questions to do. Yes. All right, so that's how the week's going to play out.